Welcome back, friends. In the previous session, we have seen, suppose if a LTI system is given, for that if the input is periodic, then the output is also periodic with the same period, or we can say same frequency. Now, let's say, suppose if it is a discrete time system, suppose if it is given what is the input, which is nothing but periodic signal, how to calculate the output. Let's take one example so that you can understand it easily. X of n is equal to 1, 2, minus 3. It is a periodic signal with a period n is equal to 3. With a period n is equal to 3. Then h of n, which is LTI system, having 1, 1, 2. Okay, 2, let's say 1. So this is h of n is given. Now we require to find out what is the output y of n. Now I told you, for LTI system, if the input is periodic, then the output is also periodic with the same period 3. So y of n, which is x of n convolution with h of n. So it is also periodic with the period n is equal to 3. Period n is equal to 3. Now, suppose if it is not periodic, we know how to calculate the output just by multiplication method. Multiplication method means we can write x of n, we can write h of n, we know the tabular method. So, to find the output in this case, which is particularly if the input is periodic, then we can perform the same convolution procedure whatever we have done in previously. That means we can take x of n, which is, let's say 1, let's say 1, 2, minus 3, 1, 1, 2, 1. So directly we can write them, and multiplication method 1, 2, minus 3, 1, 2, minus 3, 2, 4, minus 6, 1, 2, minus 3. Now if I add them, 1, 3, 1, 2, minus 4, minus 3. This is not the output. Why it is not the output? Because I told you output is a periodic with a period 3. That means we require only 3 samples, not the extra samples. That doesn't mean that we cannot omit remaining samples. What we have to do with the remaining samples is, after period, that means after n samples, n is the period, capital N is the period. After n samples, what we have to do is take the remaining samples into blocks. Take the remaining samples into blocks of size n. Of size n. So 1, 2, 3. So this is a block. Suppose there are next elements are there. Take them into blocks. Then add them here block wise. So it is nothing but 2, 4, minus 4, minus 3. If you add them, what we are going to get output is 3, minus 1, minus 2. So this is the what the output y of n. So this is the procedure. Please remember it. So here it is n is equal to 3. This is what the output. I hope you understood what I am trying to do. So we will perform the normal convolution. After that, what we will do is, we will take up to n samples. After n samples, we will take the remaining samples, or we can divide the remaining samples into blocks of size n and add it to this, and add it, and add it. I hope you understood. Take it. So I can write like this: perform normal convolution and after n samples, after n samples, wrap the remaining samples, wrap the remaining samples into blocks of size n, blocks of size n, and add it. To get y of n. To get y of n. Clear? Take it. Into. Next. So let's say one more important case in the same one. Convolution of two periodic signals. Convolution of two periodic signals, which is called as circular convolution. It is circular convolution. Circular convolution, which is nothing but convolution of periodic signal. Convolution of two periodic signals. Two periodic signals. Suppose let's say let x of n is a signal which is a periodic with a period, let's say n1, with a period n1. H of n is periodic with a period n2. Then y of n, which is convolution of two periodic signals, then we can show a special symbol which is a circular convolution, which is circular convolution. So we will write the convolution with a circle on it. So it is called as circular convolution. Whenever you see circular convolution, that means it is a convolution of two periodic signals. Then what is the period of this one? So it is also periodic signal with a period whichever is maximum of n1 comma n2, n1 comma n2, whichever is the maximum, that's what we have to take. So this is what the procedure. So here also the same thing. So let's say we can perform the normal convolution. Suppose if extra samples are there, then we can take them blockwise of size n, the period, whichever is the maximum out of it. So block size n, and we can add them. So this is what we can do in the circular convolution also. Let's take one example you can understand easily. Suppose example, let's say xp of n, that means x is a periodic signal 1 0 1 1 with a period n is equal to 4, with a period n is equal to 4. hp of n, 1 2 3 4. This is also periodic with a period n is equal to 4. Then I have to calculate yp of n. How much? We know yp of n is nothing but convolution of xp of n and hp of n, which is yp of n is xp of n circular convolution with the hp of n, circular convolution with hp of n. Then what is the period of it? Which is maximum of two periods, 4 comma 4, that is 4 only. So we are having the period of output is also 4. Now we can perform the normal convolution. What is that? We will write 1 0 1 1, 1 2 3, 4. If I do the convolution, 1, 0, 1, 1, 2, 0, 2, 2, 3, 0, 3, 3, 4, 0, 4, 4. That means 1, 2, 4, 7, 5, 7, 4. Now, what is the period of y of n, which is nothing but 4? Means after 4 samples, the remaining we have to take them blockwise. So we are having 3 only, we don't have the 4. So bring that 3 here. So we can write 5, 7, 4. Add them. So we are going to get 6, 9, 8, 7. So this is what the output yp of n, periodic output. So with the period n is equal to 4. With the period n is equal to 4. Understood? Take it. Try to see. Matrix method. Suppose we are having xp of n a, b, c, d. Let's say n is equal to 4. Period of the signal is 4. hp of n, let's say p, q, r, s. This is also periodic with 4. Then yp of n, which is a circular convolution, xp of n, circular convolution with hp of n. This can be written in the matrix form like this: A, B, C, D. This is a row matrix directly. Then we have to write the next matrix in this form: P, Q, R, S. Next row we have to start with S. That means S, P, Q, R. Next we have to start with R, R, S, P, Q. Next we have to start with Q, Q, R, S, P. So this is the way we have to write the matrix, and this matrix is called as circulant matrix, and this matrix is called as circulant matrix. Let's solve by using this method the same question what we have done now. Circulant matrix method. Let's see the same question which is taken. Yp of n is equal to 1, 0, 1, 1. Next matrix 1, 2, 3, 4, 4, 1, 2, 3, 3, 4, 1, 2, 2, 3, 4, 1. If I take it, now try to write it. 1, next 3, 2. So it is going to be 6. I hope understood. 1 plus 3 plus 2, that is 6. Next 2 plus 4 plus 3, 2 plus 4 plus 3, that is 6 plus 3, 9. 3 plus 1 plus 4, 8. 4 plus 2 plus 1, 7. So this is what the output we got. So yes, this is what the output we got in the previous case also. So circular matrix method also we can apply. So actually, so you may think that, sir, in the previous method is the easy one, why we have to go for this matrix or something like that? So we already having the easy method. Please listen. In the examination, sometimes they will give you the output is in this form. So from that you have to understand that it is nothing but the circular convolution. That means the operation between two signals is nothing but the convolution. So if they have given in the matrix form like this, so you have to understand, yes, it is nothing but the circular convolution, and these two are the periodic signals. Okay, I hope you understood. So that's why I have given you this method, otherwise not required actually. Suppose if you perform the circular convolution in the previous method, whatever we have done, that is much simpler compared to this one. Okay, take it. If x of t is equal to 0 for t less than 0, for t less than 0, and h of t exists for all t, for all t, then which of the following integral represent expression for y of t? Then which of the following represent y of t? Which of the following represent y of t? Represent y of t. Option A, integral 0 to infinity x of tau h of t minus tau d tau. Option B, integral 0 to t x of t minus tau h of tau d tau. Option C, integral 0 to t x of tau h of t minus tau d tau. Option D, integral minus infinity to t x of tau h of t minus tau d tau. So which option is correct? They may look all are same, but they are not. Why? Okay. So first listen carefully. We are having two expressions for y of t. Y of t is having two expressions. Y of t is equal to integral minus infinity to infinity x of tau h of minus tau plus t d tau. This is the one expression. Another expression, y of t is equal to integral minus infinity to infinity x of minus tau plus t h of tau d tau. So either of the expression we can use. Either of the expression we can use. Here the actual integral limits are minus infinity to infinity. This is actually true. But instead of that, they have given a different limits of the integration. So in that case, we have to see where x of t is existing, where h of t is existing. So according to that, where x of tau is existing, where h of minus tau plus t is existing. So where is the intersection limits? Because two signals are multiplied means we have to take the intersection limits, means common limits. So if you understand the common limits, that means if you multiply the two signals, we have to take where the two signals are existing. That is only the thing we have to take. So what are the two signals we have to take in this case? X of tau and h of minus tau plus t. Whereas to write this expression, we have to take the two signals and common limits for them. So what are the two signals we have to consider here? Which is x of minus tau plus t and h of tau. So these two signals common limits we have to take. So for that, let's see. First I will write like this. Here it is given x of t is equal to 0 for t less than 0. That means where it is existing, its value is equal to 0 for t less than 0. Then where it is existing? From 0 to infinity. So I can write x of tau exists between 0 to infinity, between 0 to infinity. Next, where is h of tau exist? It is existing for all the values of t. That means from minus infinity to plus infinity, it is existing. Minus infinity to plus infinity. Next, h of minus tau. If a signal is existing from minus infinity to plus infinity, if you fold it, again it is existing between minus infinity and plus infinity. So it is again existing between minus infinity to plus infinity. Next, h of minus tau plus t. Where this signal is existing, h of minus tau plus t. h of minus tau plus t means we have to delay the signal h of minus tau. So if I delay the signal by t, then definitely I am going to get again the same limits minus infinity to plus infinity. So there is no change, because if I add plus t here, it won't make any difference. Still we are going to get minus infinity to plus infinity. So we are having the two signals now, that is x of tau and h of minus tau plus t. So these are the two limits we got. So in that, which one is the common limit? That is, if I take x of tau multiplied with h of minus tau plus t, where it is existing, which one is the common limits between 0 to infinity and minus infinity to infinity? So which is nothing but 0 to infinity, 0 to infinity. So if I try to write this integral y of t, we have to write 0 to infinity x of tau h of minus tau plus t d tau. So this is what we have to write. This is the limits for integration. Next, coming to this case, x of tau exists between what points? Actually, just now we have seen 0 to infinity. And we require to find out x of minus tau plus t, where it is existing. X of minus tau, where it is existing? It is existing between minus infinity to 0. Because if a signal is existing between 0 to infinity, if I fold the signal, then it is existing from minus infinity to 0. I hope you understood. Next, x of minus tau plus t. That means we have to delay the signal by t. So if I add plus t here, so it is from minus infinity to t, minus infinity to t. And where h of tau exists? H of tau exists for minus infinity to plus infinity. So we are having the two signals now, x of minus tau plus t. So for that, this is the limits, and for this is the limits. So which one is the common limits now? X of minus tau plus t multiplied with h of tau exists for minus infinity to t, minus infinity to t. So I can write this integration y of t is equal to integral minus infinity to t x of minus tau plus t h of tau d tau, h of tau d tau. So this is what the integration limits. So if you consider this is the integrand, then we have to take this is the integration limits. If we consider this is the integrand, then we have to take these are the integration limits. So which option is correct? Option, which one is correct? Minus infinity 0 to infinity. Yeah, this one is the correct one. Option A is correct. Take it. It is also 0 for t less than 0. Then which integration will be correct? I hope it is over. You have completed taking this. Okay. So let's see both are existing from 0 to infinity. 0 to infinity. H of tau is also existing between 0 to infinity. 0 to infinity. Then where h of minus tau is existing between minus infinity to 0. We have delayed, that means we have to add t. Then it is going to be minus infinity to t. Infinity to t. So common limits between these two, x of tau and h of minus tau plus t. It is going to be 0 to t. 0 to t. So the integration will be 0 to t. In the similar manner here also, 0 to infinity. Then it is a minus infinity to 0. Minus infinity to t. Then it is a 0 to infinity. Then what are the common limits here? Again it is 0 to t. 0 to t. 0 to t. So we can take 0 to t. So if you observe carefully, if the signals both x of t and h of t are existing only for positive values of time, that means can I simply say x of t is causal, h of t is also causal. If both x of t and h of t are causal, then we are getting the limits are 0 to t, 0 to t. So this is the one indication you have to remember. In the convolution integral, the limits are 0 to t. If the limits are 0 to t, that always indicates that two signals are causal. The two signals are causal. And what is the output of that? That means what is the y of t nature? If two causal signals are getting convolved, we have seen in the convolution property, that is, if two signals are causal, then the convolution, causal convolution with causal, is again a causal signal. So I hope you understood. So this integral limits sometimes they will give in the examination also. So whenever you see convolution having integral limits 0 to t, that indicates both x of t and h of t are causal, and the y of t, which is nothing but causal convolution with causal, is again a causal signal. It's a very, very important. So I am writing that point. If convolution integral limits are 0 to infinity, comma, then, or we can say, if convolution integral limits are 0 to infinity, indicates both x of t and h of t are causal, and y of t is equal to x of t convolution with h of t is also causal. Why? We know that causal convolution with causal is again a causal signal. Okay. Sorry, not 0 to infinity. Please make a change. 0 to t, not infinity. Please make a change. 0 to t. Please make the change. It is 0 to t. It is not from 0 to infinity. the last concept in the LTI systems, which is orthogonal signals. Orthogonal signals. Orthogonal signals. Before understanding this orthogonal signals, let's talk about vectors. Vectors. Suppose it is given A bar and B bar, two vectors. When can we say two vectors A bar and B bar are orthogonal? So suppose two vectors are given to you. How can we determine they are orthogonal to each other? That means they are perpendicular to each other. Then we can simply go with if A bar dot B bar, dot product of two vectors is 0, then we can say A bar is orthogonal to B bar. Orthogonal to B bar. So this is what we can say. And you know, this product is called as dot product. Everybody knows it. And there is another name for it which is called as inner product. This product is called as dot product or inner product or inner product. So whenever inner product is 0, then we can say those two signals, those two vectors are orthogonal to each other. Orthogonal to each other. And we know, let's say, let's take two dimension, 2D. In that, this is x-axis, this is y-axis. A vector which is unit vector along x-axis is, let's call it is ax cap. And there is a unit vector along y-axis which is ay cap. If ax cap, ay cap are orthogonal, yes, they are orthogonal. Now, is there any other vector which is orthogonal to both ax cap and ay cap? No. So only two vectors, ax cap, ay cap, always orthogonal to each other, but there is no other vector which is simultaneously perpendicular to ax cap and ay cap. I hope you understood. So these are the two vectors which are ax cap, ay cap are always orthogonal to each other in the two dimension. Now, suppose let's say A bar, which is let's say 3ax cap plus 4ay cap. That means I have written a vector A bar in terms of ax cap and ay cap. Now, can I give the statement like this? In two dimension, I can represent any vector in terms of ax cap and ay cap. Yes. So I can represent any two dimension vector in terms of ax cap and ay cap. Now, what is the condition? It has to be satisfied so that I can write any vector in terms of some two vectors which are nothing but ax cap, ay cap. That means ax cap and ay cap must be orthogonal. I hope you understood. So these two must be orthogonal. If this is the condition satisfied, then we can say, we can write any vector in terms of x and ay cap. Now we can call x cap, ay cap as base vectors. We can call them as x cap, ay cap as base vectors. So x cap, ay cap, this is called as base vectors. Sometimes in mathematics they will say it is basis, base vectors. Okay. In the three-dimension geometry, in three dimension, what is a base vector set? Ax cap, ay cap, az cap. This is what is called as base vectors. Base vectors. So in terms of base vectors, we can represent any other vector. That's for the meaning of base vectors. I hope you understood. So this is about the base vectors. Now I hope you understood what you mean by orthogonal vectors. That means the dot product or inner product has to be 0. Coming here, orthogonal signals in the signals and systems. signals, what is the inner product for the signals? If they are real, if real signals, here let's say x1 of t and x2 of t are real signals, are orthogonal in the interval t1 to t2, then inner product has to be 0. Inner product. What do you mean by inner product in the signals? Inner product means integral t1 to t2 x1 of t multiplied with x2 of t dt is equal to 0. So this integration, multiplication of two signals, integration from t1 to t2 if we take, this is called as inner product. If this inner product is equal to 0, then we can say x1 of t and x2 of t are orthogonal. Okay. In the similar manner, suppose if it is complex signals, Now, if x1 and x2 are orthogonal to each other in the interval t1 to t2, then inner product is here x1 of t, x2 of t conjugate. For one signal, we have to take the conjugate dt is equal to 0. Then we can say x1 of t, x2 of t are orthogonal in the interval t1 and t2. I hope you understood. Take it. x1 of t is equal to 2, 0 less than t less than 1 is equal to 0 elsewhere. x2 of t is equal to 1 minus kt, minus 5 less than t less than 5 is equal to 0 elsewhere. If x1 of t and x2 of t are orthogonal to each other, during the time interval zero to one. Obtain constant k. This is the question. It's a very simple one. So just we have to think, we require to find out the k. That means first they have to be orthogonal to each other between 0 to 1. And they are real signals, we don't have to take any conjugate. So what we have to say is integral 0 to 1 x1 of t multiplied with x2 of t dt is equal to 0. This is the condition what we have to apply. So if I apply this condition, that implies 0 to 1. What is x1 of t, which is nothing but 2, into what is x2 of t, 1 minus kt dt is equal to 0. So if I integrate this one, 2 into 1, that is going to be t minus k t square by 2, limits from 0 to 1 is equal to 0. So if I apply the limits, what we are going to get? 1 minus k by 2 minus 0 is equal to 0. So simply k is equal to 2 we are going to get. K is equal to 2 we are going to get. I hope you understood. So this is the way we have to calculate. So this is about the LTI systems. Now I am stopping here. In the next session, we will see the Fourier series. Okay, from this topic only we will start the Fourier series. Actually, orthogonal signals. So from this is the basis for the Fourier series. Okay, so that means we are having some set of signals which are base signals. So base signals means we can represent any signal in terms of base signals. That's what the meaning of it. So we are having the base signal set, and then what do you mean by base signal set? So there is a one condition they have to be satisfied. That is nothing but orthogonality. So orthogonality is the precondition for the Fourier series. So please remember this. In the next session, so we will see what is a Fourier series. So what is the orthogonal set we are having. Okay, take it.